This video is about binary search trees, and so here's a picture of a binary search tree. Hopefully you're somewhat familiar already with the idea of a tree. You can see that there are nodes or vertices which are indicated by these little ovals in this diagram, and the nodes are linked together with arrows, which are technically called edges. And this is a binary tree, and that means that every node has exactly two children. So the nodes that point to this little dot, so the little dots stand for what are called external nodes. So just think of that as some kind of dummy node. It doesn't contain information. It's just there to sort of regularize things and make it so all the nodes have exactly two children. This thing up at the top here, head, is also a dummy node, and it just gives you, it makes it so that every node has a predecessor. So now even the root of the tree has a predecessor. So by the way, the first thing in the tree is the root, right? Okay, so all right. So what is a binary search tree for? You can see that it's a pointer linked structure, so it's sort of like a linked list. And you know, the good thing about a linked list is that it allows you to have fast insertions and fast deletions. And the bad thing about a linked list, though, is that there's no random access. And since there's no random access, you can't use binary search on a linked list. And so finding things in a linear ordered system of nodes is slow. But if you organize things as a tree instead of as a list, and the tree is organized according to, the binary search tree property, then searching becomes very fast. So in some ways, the organization of this tree is sort of a living binary search in a way that will hopefully become clear in a second. So let's just look at the binary search tree property and then see how this particular binary search tree I have here in the diagram satisfies it. So the binary search tree property says, for every node n in the tree, the following is true. So, you know, just think of, let's say that this thing is n. For every node m in the left subtree at n, so this is what the left subtree is, just everything to the left of n constitutes its left subtree. And, you know, trees have this nice recursive structure, so you can see that the left subtree really is a tree. And it's supposed to be true that for every node m, so let's just pick one. I'm just picking one at random, so let's say that that's m. So for every node m in the left subtree, it should be true that the key of n is greater than or equal to the key of m. So the key is this number here. So that's sort of like the ID number. So you're already familiar with lots of ways of organizing things into key value pairs. Like in the phone book, the key is the person's name and the keys are ordered alphabetically, and then you use the key to look up a value, which in the case of the phone book is the person's name or address or whatever. So it's the same thing with binary search trees. These keys are just what organizes the placement of the records, and then the actual content of the records isn't shown in this picture. So notice, I don't know, I hope you can see this. The key for this randomly selected m is 75,000 and some change, 75,885. The key for the root is about 81,000. And notice that it is true that the key of the root is bigger than the key of the node in the left subtree. Now, that's not true just for m, that's true for every node in the entire subtree. And that's not true just for n being the root, it's true for every single node. So if you look at this node and then look at its left subtree, every number over here is less than this number, right? Okay, so for every node, for every left subtree. And there's the similar statement about the right subtree. For every node in the right subtree, the key of the root, what you're considering to be the root, is less. So let's just see that that's true. So let's just consider this thing and consider some node in its right subtree. So there are two nodes in the right subtree of this node, and the keys are both bigger than that key, right? Or consider this one, if you will. There are two nodes over here in the right subtree, and the keys are both bigger, right? There are three nodes over here in the left subtree. The keys are all smaller. So that's the binary search tree property. That's what makes a binary search tree a binary search tree. And the consequences of that are that if the tree is nice and balanced, so by balanced we mean that for every node there are approximately as many nodes in the left subtree as there are in the right subtree. And I made this particular tree by just inserting random numbers. And so that's an important property of the whole binary search tree idea, is that if you just make up random keys and put them into the tree in random order, or you know what I'm saying, you don't have to randomize two things, just one thing. But if you insert random numbers into a binary search tree, you're probably going to get something that's pretty balanced. And we'll see later that you can get unlucky if you insert values into a tree structure in an already sorted order, for example. It's going to be really bad. But we'll see that when we talk about insert below. So binary search tree supports a lot of operations, and we're going to talk about these. These are the main ones. So the first one is insert, and insert is basically the same algorithm as search. So by that I mean, you know, let's say you want to put something into the phone book. You want to put a new entry into the phone book. First you have to find the place where the new entry should go, right? So there's not much difference between inserting a new record into the phone book and just finding one that's already there. It's the same algorithm to get to the place where you're supposed to be, and the only difference is if you're searching, then you return the value, and if you're inserting, then you plug some new information in. But getting to the place is the same. That's the first algorithm we're going to consider, and then there's an algorithm that prints the keys in sorted order. And these are all really easy, but we'll put off dealing with these until we deal with the first two, finding the minimum value, maximum value in the tree. And what if you want to know the successor of 69,000? That's like the next biggest number and predecessor. And so the only thing about binary search trees, they're really simple, except that delete is kind of complicated. So we'll put off delete until the last. It's kind of hard. Okay. So first, let's think about how you insert things into the binary tree. So I'll just give sort of a hand-wavy, you know, prosy explanation, and then we can talk about the technical details. But I think it might be helpful before we get started to look at one technical detail, which is what is a node. So I've been saying that a node is a key-value pair. So here's a key and here's a value. In practice, you know, the record corresponding to a key is not necessarily going to be just an integer. You might want it to be something more sophisticated, like a struct or some other thing. But just for simplicity, I'm going to call it an int here. And every node has, so this structure is recursive because it defines a pointer to a thing of the same type inside. So every node has a pointer, which is, we think of as the pointer to the left child. That's an L there. And it has another pointer to what we think of as the right child. So every node in the tree has a pointer to its left child and a pointer to its right child, and it has some fields for storing the key and the value. All right, so here's kind of a silly little picture. We have this tree that we started with, so just randomly selected keys. It turns out to build this tree. And the difference between these two is that on the right we've inserted the value 50,000. So I'm going to insert several values, but let's just go over how 50,000 got to the place where it is. So it was inserted into the tree. When you insert something into the tree, it's always going to end up as a leaf node, or it's going to be, both of its children are going to be external nodes. And actually that's true. All right, so how did 50,000 get to where it is? Well, you have to imagine first we put in 50,000 and we compared it to this value. And the algorithm is really simple. It just says, look, is 50,000 bigger than or less than 89,000? And if the answer is less, which it is, then you go into the left subtree where everything is less. Now you recursively play the same game here. Compare 50,000 to 36,000. 50,000 is bigger. So bigger means go into the right subtree where everything is bigger. And you recursively play the same game again. Compare 50,000 to 38,000. It's bigger, so it goes into the right subtree. Right? And now compare 50,000 to 85,000. It's smaller, so it goes into the left subtree where everything is smaller. And finally, 50,000 is bigger than 41,000, so it goes into the right subtree. And when you get to a node, when you get to one of these dummy nodes at the base, it's kind of the base case of the whole situation, and then you just plug it in. So 50,000 just gets plugged in here. So it can be kind of fun to do this. If you use alphabetical keys instead of numerical keys, then maybe we could make a binary search tree. It's a good way to practice. I'm just going to make up a word. I wanted to make up a word whose first letter comes from the middle of the alphabet, and for whatever reason, the word that came to mind was Malthusian. So let's make a binary search tree by inserting these letters one after another and using them as sort of alphabetical keys. So you insert M and it just becomes the root. Now insert A. So A comes before M, so it goes over here. Now insert L, M. So L comes before M, but it comes after A, so L ends up here. And T comes after M, so you put it in the right subtree. And consider H. So H is before M, after A, and before L, so H goes here. And U comes after T, so U goes here. S comes after M, before T, so S goes here. I is less than M, bigger than A, less than L, and bigger than H. Okay. A is less than M, and we'll just put it here as less than A. And N, L, M, N, so it's over here, less again. And if I made a mistake, just yell at me from the future through the internet, and I'll fix it. So since nobody's saying anything, I guess this is completely right. And you can see that this tree ended up being fairly balanced, but let's look at what can happen if you try to build a binary tree with keys that are not in sort of random order, but are already sorted or almost sorted. And a good word for that is abecedary. So in this word, the letters are pretty close to coming in alphabetical order. So let's look and see what happens as we insert these things. So first you put in A, and then B comes after A, so here's B. And E comes after B, so here's B. And C is to the left of E. Okay, and E, let's just put E here. And D, how does that work? So bigger, bigger, less, bigger, D, and A, let's just put A here. And R, bigger, 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 and Y, bigger, 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 bigger. Okay. So this kind of, it's really strung out, right? It has, this is a tall tree. It has a lot of levels, and you know the fancy word for the levels is the height of the tree is the number of levels. And most of the operations that we perform on binary search tree take time that's proportional to the height of the tree or the number of levels. And so if the tree is tall like this, it's almost a linked list. That's sort of the most pathological cases, is just a linked list. So if it has n nodes, then its height is n. That's the worst possible case. Then every operation on the tree takes time n, and that's bad. Okay, so compare that to what happens when the tree is balanced. When the tree is balanced, then the height of the tree is going to be approximately log n, where n is the number of nodes, and then all the operations on the tree will go much faster. And the reason we use binary search trees in practice is that when keys are selected randomly, like they are in sort of a natural situation or in a lot of situations, you tend to get a pretty balanced tree. So now let's look at how you would actually implement some of these things. And for this implementation, I'm following some ideas that I got from reading Algorithms in C by Sedgwick, who is a professor at Princeton. And we're going to use a couple of dummy nodes. And the fancy word for dummy node is sentinel, so you could say we're using some sentinel nodes. And so before we get started implementing things, I need to kind of share the basic setup with you. So first, I think a picture is worth 1,000 words. So here there are two dummy nodes. One is head, and this dummy node makes it so that every node, including the root, has a predecessor. So the root is in a special case, and that's kind of nice. That'll end up simplifying the code. And there's this other thing down at the bottom which we'll call Z. And what Z is all of these external nodes in the other picture. So you can think of all of these little boxes as really being the same box. If you tie them all together, tie all these things together down at the bottom, then you get this little sink at the bottom called Z. And he makes it so that every node has exactly 2 children, so that's kind of nice. And we'll see that he can also be kind of useful because if we're looking for a certain value, we can make it sure it's always in the tree just by sort of putting it at the bottom. So there are Z and head. So when you initialize the tree, you have to set all this stuff up, and hopefully you know some C. If you don't know C, malloc is just like new in C++, so hopefully you know either C or C++. So you've got to allocate some memory for the dummy node at the bottom, and then it links back to itself, so its left child is itself and its right child is itself. And we set its value to be -1, and head, you have to allocate some memory for that thing too. And initially the list is empty, and so you just have this head thing. So here's head. You have an empty list, and head's right child is Z, and there are no, really functional nodes in the tree yet. And both of head's children are like this. So really we're only going to have to worry about head's right child. See, in this picture you can see we only really care about head's right child. And the reason is that we're going to make head's key be -infinity. So that means whenever we can compare something to head, we're always going to go to the right. So -infinity is supposed to be smaller than any possible value. So when you're doing insertion or search and you consider head, you're always going to go to the right because the key is guaranteed to be bigger. And for -infinity in this system, I'm using int min, and that's in limits.h if you actually want to write this code. Okay. All right. So here's the actual implementation in this ugly green color. So the parameters are a key and a value. So we want to insert the key a key and a value into an existing tree. And we need some node pointers. So X is going to be sort of the current node pointer that's doing all the work. Frequently you have to remember what the parent of the current node was, and that's what I use prev for. And this is the node that we're actually going to insert. I call it toInsert. And so allocate some memory for the new node and give the new node the right key and the right value, and you're ready to insert it. So it's going to be a leaf node, or it's going to be, you know, an internal node, both of whose children are z. So we can just go ahead and set those pointers to z. And x is going to go down through the tree, like a little quarter bouncing through the Plinko game on The Price is Right. So set x equal to the root. And so this is one of the ways z can be convenient. So we don't have to, you know, worry about null point, like running off the bottom of the tree, and if z wasn't there, maybe we try to dereference a null pointer and get a segmentation error or something. By setting z's key equal to the key, we will guarantee that we eventually find a place to put the value that we're going to insert. So we can set up this simple while loop. Prev is head, so that's one of the good things about head, is every node has a parent, even the root. And we just say while x's key is not the key that we're searching for, we make the parent of x is the old x, and the new x is, so this says if the key that we're inserting is less than the current key, go to the left, otherwise go to the right. And now we just, so we found the right place. You have to imagine that we've done all this stuff and we've kind of come down to the right place. And so now we have to set the parent of the newly inserted. So this is the newly inserted node, and this is its parent. So is that a right child or a left child of the parent? And so that's what this conditional deals with. So if the key is less than the key of the previous one, then make it the left child of the previous one, otherwise make it the right child. Right, so insert is pretty simple. Even when these ideas are simple, sometimes the implementations are, you know, a little thorny or something. So now, this function is even simpler than even simpler than insert. So it just prints all the keys out in ascending order, so in sorted ascending order. And you can see that it's recursive, and sort of the root is not necessarily the root of the tree, so it has this recursive property. This is the base case. Let's deal with that last. So how do you print a tree? Well, let's say we want to print this tree. Well, we could print the left part of it, and then print out the node that we're considering, the root, and then print out the right part of it, okay, and worry about these details later. So it's a great thing about recursion. You can somehow always magically put off dealing with the complicated stuff until later. Alright, so that's how it works, but you know, eventually you keep doing this, you're going to come down to one of these last things, and if you try to print z, then that's when you'll trigger this base case and it'll just return and not do anything. So let's just kind of follow, maybe in our minds, this algorithm and label the order in which these nodes are going to be printed. So first we print left, right? Now print left again. Now print left again and return because it's z. So that'll be the first thing that we consider. So this will be the first one outputted. Now we pop back here, print this thing, and now we print right and print left, bounce back because there's nothing to do, and print him, so that's the third one. Now print right, that's 4. I'm putting myself to sleep. I must be boring the hell out of you, right? So actually we haven't printed that one yet. So we have to go down here, and I'm going to stop talking and just do this. Maybe I can chat about something else. I don't know. The thing is, this video might be on YouTube for a while, and so if I talk about something in current events, it might become ridiculously obsolete. So let's just look through this and make sure I did it right. So if I did it right, I assume I did, because I'm infallible. All the keys should be listed in sorted order. So 2000, it looks pretty good, right? So these things are, yeah, so it goes from 3 down to 4, up to 5, 6, 7, 8, 9, 10, 11, 12. Yeah, so it increased every time. So I did it right by some miracle. So That's in order print. It's very easy. Now these operations are also very easy, so I just gave you the picture of the tree again, so let's go through and do these things. So how about min? So let's say you want to find the smallest, the element with the smallest key in the tree. It's a really stupid algorithm. You just go left until you can't go left anymore, and that gives you the minimum key element in the tree. So I'm not even going to give you code for that because it's just obvious. Just go left until you can't go left anymore. And that probably gives you some ideas about how to do max, how to find the maximum element in the tree. Well, I'm sure everyone is shouting out at home in the future on the internet that you just need to go right as many times as you possibly can, right? And that gives you the maximum key, and which in this case is about 160,000. Okay, so max and min, very easy. Alright, and so predecessor and successor, I kind of throw those in because those are going to be important for the delete operation. So let's say I want to find the successor to the root, which is 89,000. You go to the right once, right? So that makes this thing is bigger now. But once you've gone once to the right, you want the minimal thing that's bigger, right? So just go to the right and then find the minimum in this subtree. So the minimum in the subtree of things bigger than the root is going to be the successor. So go right once, then go left as far as possible. So the successor of 89,000 in this tree is this one, which is 90,000. And so predecessor works really similarly. You want the maximum element in the subtree with smaller keys. That will be the predecessor. So that means go left once and then go right until you can't go right anymore. And so you stop here at 85,000. So 85,000 is the predecessor of the root, which is 89,000. So really kind of beautiful thing about binary search trees. It works like that. Okay, so I think we have to come to grips now with delete. So I don't know why. I'm trying to think of some philosophical reason why delete should be hard. I can't think of one. So here's the basic plan. I hope it makes sense. So I'm breaking it down into a few cases. One is that the node that you want to delete is sort of toward the bottom of the tree. So let's say we want to, delete this guy. Then, he's also going to be connected in somewhere, like he has a parent too. And so if he's pretty close to the bottom of the tree, like this guy just has, he's a close relative of Z. So I'm thinking of this thing as being Z. And so the first thing I'm going to consider is that the node to delete is a recent ancestor of Z. Like this guy is a close relative of Z, because Z is his child. In this case, you can always splice it out locally. Like, what does that mean? Well, in this case, you could just forget about this guy and then make this the left child of the parent of the thing that we deleted. So you can do some splicing with the pointers, and what's going on in the tree, globally with nodes far away is irrelevant. So you can just locally fix things up by splicing. You can always do that if a node is a recent ancestor of Z. If a node is a distant ancestor of Z, then you have to do this trick. And the trick is to replace the node with its successor. We just talked about successor, remember? And delete the successor. So the successor is always a parent of Z. And why is that true? Let's go back here and do a little reminder here. So this was the successor, right? The reason the successor has to be a parent of Z is, well, you can't go, that's one of the things that characterizes being a successor is that you can't go left anymore. And the reason you can't go left anymore is because Z is always to the left, and so Z is always a left child of the successor, and similarly Z is always a right child of the predecessor. So these will be local splices. So it's easy to splice out the successor. And notice if we replace this with its successor, then the binary search tree property stays true. So it'll still be true that everything in this tree is bigger than or equal to this thing because it's the successor of what was formerly here. So if anything were smaller than this, it would have been the successor. And convince yourself for similar reasons that it would also be okay if we replace this thing not with its successor but with its predecessor. You know, successor, predecessor is kind of symmetric. So if we crossed this out and replaced it with its successor, 85, 386, and then spliced out this 85, 386 thing, then this structure would still satisfy the binary search tree property. What do I have to assure? I have to assure that everything on the left is really smaller than this, but of course it is, because if anything were actually smaller, it would have been the predecessor, right? Okay. I'm glad you agree with me. I was worried that you would put up a big argument. Okay, so that's what this is saying. Replacing the node with the predecessor rather than the successor works just as well. And in practice, you want to randomly alternate between these to preserve the balance of the tree. This is getting to be kind of a mess here. So imagine what would have happened if we had just if we just replaced it with a successor every time. Eventually we would drain, if we just kept deleting the root, we would drain this right subtree and we would make the tree unbalanced. And one way to stop that bad thing from happening is to randomly alternate between replacing the node with its successor and replacing the node with its predecessor. So that's the plan. Okay. Alright, so here are some examples, and in this example I write this is the same tree as this. The difference is I'm going to repeatedly remove or delete the root until the tree is empty. So I'm going to delete 89,000, this thing right here. And what is it going to get replaced with? Well, my algorithm, it has a little bit of randomness because it randomly decides whether to replace it with the successor or the predecessor. So let's see. The algorithm replaced this thing with that. So what is that? That's the predecessor, okay? So what happened when we went from here to here, this node was deleted, it got replaced with its predecessor. And what happened where its predecessor was? Well, the predecessor got locally spliced out. Now 335 connects directly to 41,421. So just a little local, pointer reassignment fixes that. Now you also had to connect 85, 386. So you have to know not only the thing that you want to delete, you also have to have control over its parent because you have to fix up its parent. All right, so you have to set it so that the head now points to this new guy. So now we're going to delete this guy, and what goes in for him? 9,000 or 90,000. So now this guy is going to get replaced with his successor, and the successor is just going to poof because he has no children. And so this is where that successor used to be. And now we're going to delete this guy. He gets replaced with this, which is his successor, right? And the successor gets spliced out. So now it goes straight like this over in the new tree. And he's here now. This guy is gone. Now we're going to delete him. And he gets replaced with 50,000. 50,000 is his predecessor. So go left once and right as far as you can, and you get to 50,000. So 50,000 replaces him. And now what happens? 41. So he gets replaced with his predecessor too. So he gets replaced, the predecessor. Now you can see that this is just that, right? And this thing gets replaced with 38. So that's the predecessor. 38 gets replaced with 36, and 36 is the predecessor. It's spliced out. And now 36 gets replaced with 23. So what is that? That's because 2,362 is the predecessor. And we've been doing a pretty good job up until now of maintaining balance in the tree by doing this random alternation we got a long run of predecessor choices, but that will happen. This is a small tree, and so if for a big tree, that having 5 predecessors in a row is no big deal. But for a small tree, it's sucked the left subtree dry. So now we have this bad linked list situation, and now they just get gobbled up one by one. So successor, 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 and the tree is now empty after this. Okay, all right. So now the devil is kind of in the details. It's really not very complicated, right? Everybody can kind of, now you have to say exactly what splicing means and other stupid things like that. So this is my implementation, and hopefully it's not too complicated. I use this term anti-successor, and the reason I worry about the anti-successor, so let's consider this one of these earlier situations. So between here and here, the root got replaced with his successor, which was 92,777. Now, where 92,777 was, you have to have control of his parent, because when you splice him out, his parent has to now connect to his right child. See, that's what's happening over here. So I call this the anti-successor. This is the node that comes before the successor. And yes, I am inventing terminology in my explanation. Sorry, but I had to call it something. Okay. All right. So let's see how this works. So we want to delete the node whose key is that. So this first part of the code is just about walking down to where this guy is. So if you understood insert, then this is all going to be very boring for you. So make z the key, that's so we don't run off the bottom, and the prev is going to be the parent of x. X is going to wander down the tree. So initially x is the root, and well, the key of the thing you're looking at is not the key that you want. Make the old x be the parent of x, and now set x equal to go left if the key is smaller, go right if the key is bigger. So you're just wandering down the tree, just like Plinko and The Price is Right, until you get to the appropriate place. So now we're at the appropriate place. X is now the appropriate thing to delete. And what now? So this is the random choice between going left or going right. With the return value, I want to put off talking about what delete R does. But what this is the thing that goes in X's place. So when we were doing these warm-up exercises with the deletion, something always goes in the place of the thing that got deleted, right? Like in this case, this one gets deleted and this guy goes in its place. And that is what this x value that gets returned by the delete function is. It's the thing that goes in the place of the thing that just got deleted. And now this connects things up with the parent of the thing that was deleted. So if the key of the thing that goes in place of the thing that was deleted is less than the key of the parent, then make him a left child of the parent, otherwise make him a right child of the parent. Okay. So he's going to be the same kind of child that X was. If you can think of some more elegant way to express that, then you can do it that way. All right. So what is this helper function delete R? So this is basically, in sort of the generic case, it's going to replace, we're going to go into the right subtree, and who lives in the right subtree is the successor. So you can think of delete R, this is just the case where we replace X with its successor. Now in the beginning we have to deal with some irritating special cases which happen when the right subtree is small. So let's consider the case we're deleting this guy. It might be that the right subtree is just Z, right? So that is what this case is. So if and here you have, some normal left child, and the tree goes on. So we're deleting him, and so if the right child is Z, then you just push this up like this, and then back in the other function we'll fix up the parent connection, and by replacing X with its left child, that will just take X out of the tree. Now what this first line does is it saves the original X, so that before we exit this function we can free it. So don't forget to do that, or you'll get a memory leak. So we splice out this thing, which is the node that we were going to delete, and then free its memory. Alright, so we've dealt with a case where the right subtree is just that little nubbin. Now, what else can happen if the right subtree is small? So this is another sort of special case here for, and this is if X is its own anti-successor. So you need to manipulate the anti-successor and also manipulate X at the same time. So I have this special case where this is the thing that you want to delete, and what if its right child's left child is Z? So in that case, this thing is the successor of the thing that you want to delete, and X is its own anti-successor. And what do you want to do in that case? You just want to replace this with that, right? So X is equal to its right child, so that replaces this with that. And you make the left child equal to, so now you want, when you make this guy sort of move in up here, now he's going to get a left leg, and his new left leg is going to point to what X's left leg pointed to, and that's what this is dealing with. All right, so the picture is getting kind of busy, so maybe you can delete some of this stuff. Right, and let's deal with this generic situation where the right subtree is big and deep, and this is what will get called the most often. So you find the anti-successor. So let's try to draw a picture of that. So we go right, and then we go left a couple of times maybe. And so let's say that this guy is the successor, right? This would be the successor. And S is going to be the anti-successor. So that's the thing right before the successor. Now you do, and now X is here, right? X is this guy. So you make X equal to S left. So that's him. So that's going to make this guy go up here. And now you do S left is equal to S left right. So what that's doing is it's hooking the anti-successor's left child link has to be put down here because this guy is getting spliced out. So that's what this line does. Now you say X left is equal to, okay, so this is a little bit confusing because now X has been set to S left and S left has been put up here. So X left is going to be this pointer after this guy has been moved up, and that should be a pointer to what the old X, so here's the old X, he's kind of an angel now. He has angel wings, or maybe he went to hell, I don't know. And here's his halo. So that's what temp is, and he used to point here, and so the new thing that goes there is also going to point there for its left child. And yeah, so you also need to hook up the right pointer the same way. So this guy used to point somewhere, and now the right pointer of this new thing needs to go to the same place. Alright, now free the memory and return the new thing. And that's it. I'm not going to give the code for the anti-successor. It's easy. And now we know pretty much every interesting thing there is to know about binary search trees. Okay. Thanks for watching.